Good day, class, and welcome back to my calculus class. Today we will be looking at the squeeze theorem. Before that, let us take a look at the following problems. If I want to evaluate the limits of this function, 1 divided by 1 plus sine of x, as x goes to 0, let us use the usual method we have been using. Now I can say this is equal to 1 divided by 1 plus sine of 0. So, which is 1 divided by 1 plus 1. I can do that because the whole function is continuous. We will talk about continuity very soon. And this gives me, this is 0. Sine of 0 is 0. Remember, on our unit cycle, this is where we have angle of 0 and the terminal point there is 1, 0. So the sine of 0 there is 0. So in this case, we have 1 divided by 1, which is 1. Okay, we can do that. Fine. Let us go to the other problem. Question number 2. In this case, we have sine of theta divided by cosine of theta as theta goes to pi. So again, let us do this. Sine of pi divided by tangent of pi. What do we have? This is where we have angle pi, and the terminal point there is -1, 0, meaning that sine of pi is 0. And in that case, we have 0 divided by, what of tangent of pi? Well, tangent of pi is the same thing as sine of pi divided by cosine of pi, which is 0 divided by -1, and it is 0. So it turns out that we are having the case of indeterminate form. Indeterminate form. Now, what can we do in this case? Well, let us see if we can simplify the trig function. We can say limits as theta goes to pi of sine of theta divided by tangent of theta is the same as limits as theta goes to pi of sine theta. So I will rewrite tangent as sine of theta divided by cosine of theta, which is the same thing as limits as theta goes to pi of sine of theta times cosine of theta divided by sine of theta, which we can say here 1, here 1, and we do have, this becomes limits as theta goes to pi of cosine of theta. And now we can throw in our value for pi there, for theta rather. So we have, in this case, we have cosine of pi if I substitute. And remember, cosine of pi is -1. So we have that as our answer. Okay, that is good. Let us move on to the next one. In this case, we have limits of this function, x squared sine of 1 over x, as x goes to 0. In this situation, we would have, if we go by what we do know, we will have, okay, Let us substitute directly. We have 0 squared sine of 1 will be in a situation that we cannot handle because now we are dividing by 0, which is not the right thing to do. And it doesn't seem like we can simplify this function as we did with sine of theta divided by tangent of theta earlier in this problem B. Now, what can we do? Well, we need to learn something special now, and that is the idea of squeeze theorem. Okay. Now, the techniques we have developed thus far worked very well for algebraic functions, yes. But we are still unable to evaluate limits of very basic trig functions like in problem C. The next theorem, called the squeeze theorem, proves very useful for establishing basic trigonometric limits. What does it mean? I mean, what does the theorem say? It is very simple. It's saying if we have a function, say f of x, and that function, the function's y value, say for example at this point, look at it at this point, it is less than the y value for g of x, and it is less than the y value for h of x. So we say this function f of x is less than, let's say, g of x, and it's less than h of x, or at most, they are the same. Now, if that happens, and we can compute the limits of the extreme guy here as x goes to, let's say, a, let's say it is some real numbers, L. And let's say we compute the limits as x goes to that same point A of the other extreme function, h of x. And it is also the same as L, that our real number for the limit of f of x. Then we claim that the limits as x goes to that same point A of the function in the middle will be forced to be the same as L. It is the same thing, just as we have in this diagram. So the function g of x is squeezed. Some textbook will use the word pleased. It is pleased. It is sandwiched in the middle, squeezed into the middle. So it cannot, the limits as the input goes to this point A, I cannot go beyond what the limit of the higher functions and the lower functions, because it has been squeezed in the middle. So that is exactly what I have here. We have the functions behaving this way and their limits behaving this way. Then we claim that the function of the middle function, the limit of the middle function will be the same as n. Let us take example. Look at this function. We have 2 plus x minus x squared. 2 plus x squared. They are two different functions. And the question is for us to find limit of the middle function f of x. We don't even know what that function is. All what we need to do is to find the limit of this first extreme function as x goes to 0 here, as x goes to 0 of 2 plus x minus x squared. And since this is a polynomial, we can just substitute, and that is 2 plus 0 minus 0 squared, which is 2. Then we do the same for the other extreme value as extreme function, as x goes to 0. So 2 plus x squared. Again, it is a polynomial, so we have learned that we can substitute directly, and it is 2. Now we observe that the limits of the functions, the first and the last, the limit is the same, it is 2. Then we can say, then by squeeze theorem, we need to put this by squeeze theorem. Limits as x goes to 0 of that function is also 2. That is our claim. All right. Now let us return to the problem we're trying to solve the other time in C. Now we have this situation. This situation is not written as we have here. We already have the lower function, the upper function. We just evaluated their limits. In this case, we do not have the lower function or the upper function. We just have the function. We are looking for its limits. Now, what do? We need to find a lower function and an upper function. How do we do that? It is very simple. Let us go back to what we used to know about sine function. Recall that the range of sine of x is -1. We have it this way. I will write it this way. So remember, sine of any angle behaves this way. It is between -1 and 1. The sine of any angle. So 1 over x is any angle. So that is why I can write that. Now, what can we do? Look at what we are looking for. It is having something else here. So we can multiply through, that is everything, by x squared. Now we need to be careful here when we multiply. Now, look at something. If I have, let's say, 2 and 3, I can say 2 is less than 3. Agreed? Now, if I multiply everything here by -1, for example, what I'm going to have is -2 is less than -3, which is not true again. It is wrong because -2 is now greater than -3. So it then means when I multiply by -1, by negative, I need to switch. And it has to be -3 now is less than -2. That is what I should have. However, if I multiply by a negative number, let's say -1, 2 less than 3. But if I square it, that square is going to turn this -2 positive, meaning that this inequality will be preserved because the square has cancelled out the negative. So I will still have 1 times 2, which is 2, 1 times 3, which is 3, and 2 is still less than 3. Now, since we are multiplying by the square of x, then there is no problem with our inequality. We will just have x squared multiplied by -1 less than sine of 1 over x less than 1. And that is -x squared is less than x squared sine 1 over x less than equals to x squared. So the inequality is preserved. Now, what do we have next? Observe. We observe that the limit, as we are looking for x goes to 0, as x goes to 0 of negative x squared is 0. And the limit as x goes to 0 of x squared, the other function, is also 0. Oh, they are the same. Then by squeeze theorem, limit as x goes to 0 of x squared sine of 1 over x is also 0. And that is our answer. Okay. I hope that makes sense to us. Moving on, let us look at the next example. Okay. We want to evaluate the limits as x goes to 0 of the function x multiplying by e raised to power cosine of 1 over x. Again, we will see that we will be having problem if we substitute 0 for x over there, because now we will be dividing by 0, which is not supposed to be so. Now, let us use the idea of squeeze theorem. Recall that, again, minus 1 is less than equal to cosine of 1 over x, less than equals to 1, right? Since minus 1 is less than equals to cosine of x, or theta, less than equals to 1. That is, the cosine of angle fall between -1 and 1. So whatever that angle is, that inequality is still preserved. So that is why we can write this. Now, let us see what we can do. The first thing is, let us multiply by an exponent. Okay, an exponent is a value of 2.7 and so on. Okay, approximately, which is a positive number. Now, if we multiply through, that means the inequality will be preserved. So we can say multiply through by exponents, by e, which implies that we have e raised to power -1, that is -1 times e times, that is e times -1. So we have e raised to power -1 less than equal to exponents of cosine 1 over x less than equals to exponent of 1. We are taking exponent through. Let me rewrite this. So taking exponents throughout. Okay, now that is because if we are multiplying by exponent, then this will be -e. So instead, we are taking the exponent of everything we have there. That is, we are erasing whatever we have there by exponent. So that is what we are doing here. Okay, now that we have, since see the behavior, okay. Now, what do we need next? We need x to be in our function. We need x to be in our function. What can we do? That is, we need to multiply by x. But like I showed you the other time, if we multiply by x, say we do not know what kind of x we are multiplying with. Remember, we are taking limit as x goes to 0. And from the definition of limit, it is from the right and from the left. That is, we need to consider every possible value of x as x goes to 0. Now, it turns out that if we are multiplying by a negative number, our inequality has to change. If we are multiplying by a positive number, the inequality is preserved. Just like I explained in the case here. Because we're multiplying by x squared, so that was why we did not have any problem. Because the square is going to cancel out the negative. It will turn it back to positive. But in a case whereby we are only multiplying by x, then we need to consider two cases. So I will call it case 1, when x is less than 0. That is when x is negative. So multiplying through, let me first write multiply through by x. So we have case 1. Case 1, that is when x is negative. And when x is negative, it turns out that we will have x e to negative 1 greater than equals to x e to cosine of 1 over x greater than equals to x e raised to power 1, which is x e. I hope that makes sense. Let me show you an example. I already did, but let me show you 2, 3. So if I multiply by negative 1, for example, if this is less than 2, and I have minus 2 less than minus 3, this is wrong. So since I multiply by negative, this has to switch to this side. So that is why I taught the inequality. The inequality is not preserved when we are considering a situation when x is less than 0. And now, again, if we have that negative 2 is greater than negative 3, which is the right thing, it turns out that I can also rewrite this now and say negative 3 is less than negative 2, which is true. I can swap it. Now, using that idea, it implies that I can start from here now and say xe is less than xe cosine 1 over x less than xe to negative 1. So because I want it to be in that form to mimic what we have from squeeze theorem, because we want to use squeeze theorem, right? We want it to be in this form. Okay, now that we have our inequality set up the right way, now let us take the limit as x goes to where? We are looking at 0, okay, 0. As x goes to 0 of x e, and that is 0 times e, which is 0. Also, limit this one now as x goes to 0 of x e to negative 1, that is 0 times e to negative 1, which is also 0. Now, what can we conclude? We can say that we can now say that the limit, it is now safe to say, therefore, by Squeeze theorem, the limit as x goes to 0 of xe cosine of 1 over x equals to 0, since they are the same thing. We are not done. Remember, we've only considered when x is less than 0, which is the same thing as saying we are considering the lower limit, the limit from the left. Now, case 2, let me write it here. Okay, case 2, when x is positive, So when x is positive, I'm multiplying everything here by x. Remember, since x is positive, so the inequality is preserved. So I will have x e to negative 1 is less than x e to cosine of 1 over x less than equals to x e to the 1. And then we have our inequality set up the right way, which means we can take the limit as x goes to 0 of x e to negative 1, which is 0 times e to negative 1, which is 0, limits as x goes to 0 of x e to the 1 is also 0. Then, by Squeeze theorem, limits as x goes to 0 of x e cosine of 1 over x is equal to 0. So in fact, here I can put this here to show that this is from the left and this is from the right. Therefore, thus, limit as x goes to 0 of x e cosine of 1 over x is 0. So that is the complete solution to that problem. Let me revisit what I did here the other time. Look at what we have. We have x e raised to power cosine of 1 over x. So what we do is we started with this inequality, which is true. And then we say, take the exponent of everything, not multiply by e. Take the exponent of everything, which makes it become e to negative 1 less than equals to e to cosine of 1 over x less than equals to e raised to power 1. Then we say we need to multiply by x. But since x is not having squared, it means we need to consider when it is negative and when it is positive. So we consider case 1 when x is negative, and we also considered case 2 when x is positive. So I hope that makes sense to you. Okay, so using that idea, you can pause this video now and try to solve this problem by applying Squeeze theorem. Do not forget, this is x again. You need to consider two cases, since if you multiply by x, which is negative, it is going to affect the inequality. All right. Now, we now use the Squeeze theorem to tackle several important limits. We begin by finding the limit of sine of theta as theta goes to 0. Consider this diagram. Remember from unit circle, let us return to unit circle. We have this. Now, if we have this angle, and we call this theta. So the angle here is also the length we're having here, which is theta, right? Now, if we have this, remember we call this place cosine of theta and we call this place sine of theta. We have that. Now, from this is where our angle is 0. Here is 90, theta. And by the time it gets here, we have 90. So meaning we can say for 0, which is less than theta, and theta is less than 90, pi over 2. That is, from 0, 0 is less than theta, theta is less than 90, right? So we can say for that inequality, we can say that the y value, 0 there, because here is a 1, 0, right? So we can say the y value there, 0, is less than this y value here, which is sine of theta. It is less than that. And if you see, that length will be less than this arc length, which is also theta. So we can form this inequality. But then observe that in this case, we are considering, if we say, let us find the limit as theta goes to 0 from the right. That is, we want to see when this, let me use another color, when this angle theta goes to 0, right? When that angle theta goes to 0, we want to look at the limit. That is the limit on the positive side. So we do have, see, limit as theta goes to 0 from above of 0 is 0. Also, limit as theta goes to 0 of angle theta is also 0. Then, by squeeze theorem, by squeeze theorem, we can claim that the limit as theta goes to 0 from above of sine of theta is 0, since we have looked at both sides. Similarly, if we consider the same arguments and say as theta goes to 0 from this side, as theta goes to 0 from this side, similarly, I will just say similarly. That is using similar argument. Similarly, we obtain that the limit as theta goes to 0 from the left of sine theta is 0, which implies that the limit as theta goes to 0 on both sides now of sine of theta is 0. So this is a very important result in calculus that we must hold on to as from now onward. Do not forget that. A direct consequence of that is also to find the limit of cosine of theta. The limit of cosine of theta as theta goes to 0, which is, we can recall the Pythagorean identity, which is cosine squared of theta plus sine squared of theta is 1. You shouldn't forget this at any point in time. Now, cosine squared of theta is 1 minus sine squared of theta. I can do that, and I can take roots, squared roots on both sides. Then I will have cosine of theta. It is supposed to be plus or minus, but I will consider just positive because I'm considering working in the first quadrant. In fact, when you consider even here, cosine is also positive here. So we do not have any problem with that. So now we have squared roots of 1 minus sine squared of theta. Please, in this class, you should not have 1 minus sine of theta as your answer. Say square root of 1 is 1. Square root of sine squared theta is sine theta. No, that is not true. You shouldn't be having that because of the negative you have in between. Now, let us see if we can use some of the ideas we had earlier. Limit as theta goes to 0 of cosine, let's say taking the limits, as theta goes to 0. So, of course, sine of theta equals to limits as theta goes to 0 of square root of 1 minus sine squared of theta. And remember from our limit laws, this is equal to, I can move the limit inside the square root. So I have this 1, and I can also write it this way because that is from the difference limit law or difference law for limits. So sine squared of theta. This is square root of 1. Remember, limit of a constant is that constant. So 1 minus, I can rewrite this as limits as theta goes to 0 of sine theta times limit as theta goes to 0 of sine theta because it is sine squared theta. And that is square root of 1 minus. From what we have here, we have claimed that that value is 0. So we can just use it there. That is 0 times 0, which is 0. And our answer is square root of 1, which is 1. Therefore, our claim is the limit as theta goes to 0 of cosine of theta is 1. So in general now, we know that, so you shouldn't forget this, limit as theta goes to 0 of sine theta is 0, and limit as theta goes to 0 of cosine of theta is 1. You shouldn't forget these two powerful results. Next, we take a look at a limit that plays an important role in later chapters that we are going to be considering in this class. And that is limit as theta goes to 0 of sine of theta divided by theta. It's a very useful function. So let us get that result. Again, we return to the unit cycle. Let me make a better one. Okay, maybe that's good. The unit cycle. Now, again, I will do what I did exactly the other time. I have this, I have this, I call this side theta. I remember that means from here to here that arc length, I can call it theta, the angle subtended. Okay, now I can make this, I want to just doing something like that, and I can do this. Okay, now remember from above here, we claim that A is sine of theta. So yeah, the y value. So here is sine of theta. Here is sine of theta. This arc length here is theta. Now, let us find something for this long length that we find here. Now we have something, not that, something like this. So here is theta. Now, this is the side opposite to this angle theta, right? So, what can we say? This is opposite. And remember, from here to here, we know it. It is 1. Since it is a unit circle, it is 1. So what will this height be? That is opposite. This is adjacent. So we use tangent from SOHCAHTOA. Remember, from this SOHCAHTOA. So opposite and adjacent. So that is tangent of angle theta is opposite, which is h, over adjacent, which is 1. That implies that h equals to tangent of theta. So we have this place to be tangent of theta. Now, what can we say? Again, for our angle starting from 0 less than angle theta, which is less than pi over 2, that is in that first quadrant, we observe that, what do we observe? Sine of theta, that is this length, is less than this arc length, which is theta, and this arc length is less than the long guy that we have found to be tangent of theta. That is very true. Now let us see something. Let us manipulate, or let us manipulate what we have here. So I will just start it from sine of theta less than tangent of theta. We can divide through by sine of theta. Divide through by sine of theta, and I will have, that implies I will have sine of theta divided by sine of theta less than theta divided by sine of theta. Since I'm dividing by the same quantity, so it is preserved, divided by tangent of theta divided by sine of theta. Okay, now this implies that I will have 1 less than theta divided by sine of theta less than, let us simplify that. Tangent is sine of theta over cosine of theta divided by sine of theta. So which is sine of theta divided by cosine of theta times 1 over sine of theta. So here 1. So I have 1 over cosine of theta. Now, what can we do? Remember, I'm looking for something like this. Limit as theta goes to 0 of sine of theta divided by theta. But what I have is theta divided by sine of theta. Well, let me quickly show you something. I want to manipulate that inequality again. So let me show you something. If I have something like this, let's say 2 is less than 3. If I take the reciprocal of this guy, that is 1 over 2 and 1 over 3. What do you think about the inequality? Will it still be less or will it be greater? Let us find out. Decimal is very helpful. This is 0.5. This is 0.33 and so on. So meaning that this is now greater. It is no longer less. Let me apply the same thing here. Taking the reciprocal, since I know what I'm looking for. So that implies reciprocal of 1 is 1. Now my claim is that it will be greater than the reciprocal of theta over sine theta will be sine of theta over theta, which will now be greater than cosine of theta. Reciprocal of 1 over cosine of theta is cosine of theta. So from this that I showed you, that inequality holds. Now, I want to write it in a way that it will be similar to using, squeeze theorem. So this implies that I can say cosine, we have used something like this here today. Cosine of theta is less than sine of theta, or theta less than 1. Therefore, taking limit as theta goes to 0 of cosine of theta is, so that is cosine of 0, so which is 1, right? On the unit circle, this is where we have 0 and it is 1 comma 0 there. So x there, which is cosine, is 1. Similarly, limit as theta goes to 0 of this other guy here, 1, is, well, it's a constant function. It is 1, which implies that by squeeze theorem, limit as theta goes to 0 of sine theta over theta is 1. Now, look at what we've done. We have only considered as theta goes to 0 from above. So we still need to consider on the other side as theta goes to 0 from the other side. So I will just say, let me move this. Okay, so I will just, meaning that what we have considered here is from above, from, okay, okay. So I can say this is from above, from above, from above. So I would just say similarly, that is from similar arguments, similarly. You can try to just look at that. It's the same thing that we have done, just from the inequality. And in this sense now you are considering negative pi over 2, for negative pi over 2 less than theta, less than 0, you form the inequality. And yeah, so similarly, we claim that the limit as theta goes to 0 from the left of sine theta over theta is 1. Therefore, limit as theta goes to 0 of sine of theta divided by theta, that is the double-sided limit, is 1. This is another important result that we must not forget. We have so many important results today. We have 3 of them. Do not forget. Limit of sine of theta as theta goes to 0 is 0. Limit of cosine of theta as theta goes to 0 is 1. And limit of sine of theta divided by theta as theta goes to 0 is 1. Please do not forget. Making 3. Now let us apply our new knowledge to solving this problem. Again, look at it. This function is not defined when theta is 0, so I cannot substitute in that regard, because I will be having a case of 0 over 0, which is indeterminate form. Indeterminate. So let us see what we can do. In this case, I will need to do something. We have not seen this before, so let me show you. I need to rewrite this function in a way that I can use the results I have earlier. So this is the same thing as limits as theta goes to 0 of 1 minus cosine of theta divided by this multiplied by, I'm going to multiply by the conjugate of this 1 minus cosine of theta. That is 1 plus cosine of theta divided by 1 plus cosine of theta. Let us see how that helps us. So that is limits as theta goes to 0. Limit as theta goes to 0 of, if I am having 1 minus x multiplied by 1 minus x. So my result should be 1 minus x squared. So in this case, my result is 1 minus cosine squared of theta using difference of 2 squared. And at the denominator, just like we have learned in the past, we will not try to multiply it. We'll just leave it the way it is. So equals to limits as theta goes to 0. So remember, I can write the numerator as sine squared of theta. So divide by theta into 1 plus cosine of theta. I can do that. Now, look at this. I can say this is limits as theta goes to 0 of sine of theta divided by theta times sine of theta divided by, I've used that theta, so divided by 1 plus cosine of theta. Look at the way I try to separate things out because I know that I know this. So let us see if that helps us. Remember that I can write this as limits as theta goes to 0 of sine of theta over theta times limit, since I'm multiplying the functions, sine of theta divided by 1 plus cosine of theta. Let us see if that will help us. Well, this is equal to, this case, we know it is 1. So this is 1 times, what about here? Well, this function is defined when theta is 0 because cosine of 0 is 1. So that is, and if we do this, sine of 0 is 0, or we can just say limit of sine of theta as, look at it, limit of sine of theta as theta goes to 0 is 0 divided by 1 is 1 plus limit as theta goes to 0 of cosine of theta is 1. So that is 1 times 0 divided by 2, which is 0. So our answer is 0. Okay. Now, I hope that makes sense to you. It is interesting in a way. So now, I want you to pause this video and try this problem out. Your answer should be 1/2. So this is what you should be having. So try to solve it. Make sure you show every step. And this is where I'm going to be ending this particular video. And I will see you in the next video. So I hope you enjoyed this class. See you and bye for now.